Dear students, in today's class, we are going to discuss about binary search tree. A binary tree is a tree where each node can have at most two children, one in the left, other in the right. A binary search tree is a special type of binary tree with the following property. So the property says that all the nodes which are in the left side of a parent node will always have a lesser value than the parent node. And all the nodes that are in the right side of a node will always have a value greater than its parent node. And this property is applicable to all the internal nodes in a given tree. Look at this example where 25 is the root node with two children, 20 in the left and 36 in the right. Similarly, 20 is an internal node with 10 and 22 as its children. So, if you look at all the left children of 25, they have the value lesser than 25. If you look at the right subtree of 25, they all have the value greater than 25. And this is applicable to all the internal nodes, namely 20, 36, 10, 30, 40, 5, 12 and 48. So the binary search tree ADTs, or what are the operations that can be performed on a binary search tree are: you can create a binary search tree when n elements are given. So if you have created a tree and if you want to insert one more node, so insertion can be done in the binary search tree. Similarly, when you want to delete a node, so three cases are possible. One, deleting a node which is in the leaf level. Second one, deleting a node with one child. And the third case is deleting any of the internal node where it has two children. Similarly, searching can be done in a binary search tree. Traversal is visiting all the nodes in the given tree. So we have breadth first traversal and depth first traversal. In the depth first traversal, we have in-order traversal, pre-order traversal and post-order traversal. We can find the minimum element in a given tree and we can find the maximum element in a given binary search tree. So let us look at each ADT in detail with example. So the first ADT is creating a binary search tree from n elements. So let us have a look at how to create a tree that holds the binary search tree property. So consider this example. Create the binary search tree using the following data elements. Around 9 elements are given. We start creating the binary search tree one by one by making one insertion at a time. Every time we insert, we need to ensure whether binary search tree property holds good. That is, a node can be inserted by comparing the root element. If the element to be inserted is lesser, it has to be inserted in the left side of the node. If the node to be inserted is greater than the node, then it has to be inserted in the right subtree. So to begin with, the first element to be inserted is 43. Initially, the tree is empty. So we insert 43 and 43 will act as the root node as well as the leaf node as of now. So step 2 is to insert the element 10. 10 will be compared with the root element. Since 10 is lesser than the root element 43, it will be inserted in the left side of 43. So moving on to the third insertion, element 79 to be inserted. 79 will be compared with the root node. Since 79 is greater than 43, so 79 will be inserted as a right child of 43. The next element to be inserted is 90. So in step 4, 90 will be compared with the root element. Since 90 is greater than 43, it moves to the right side of the 43. As already 79 node is there, 90 will be again compared with the 79. Since 90 is greater than 79, 90 will be inserted as right child of 79. So moving on to the next insertion, step 5, we have the element 12. 12 will be compared with the root node. Since 12 is lesser than 43, 12 has to be inserted in the left subtree. Since already there is a node with the number 10, 12 will be compared with 10. Since 12 is greater than the already left child 10, 12 will be inserted as a right child of 10. So in the same way, the next elements will be inserted based on comparing from the root node, and the element to be inserted will always get inserted at the leaf level. So proceeding further, the next element to be inserted is 54. So 54 will be compared with the root node, compared with the 79, and it will be inserted as a left child of 79. So the next element to be inserted is 11. So in step 7, 11 will be inserted as a left child of 12. So this is the procedure to create or to build a binary search tree when n elements are given. So the only thing that needs to be kept in the mind is for each element, it has to be compared with the root, and accordingly, if it is lesser, it has to be inserted somewhere in the left subtree. If it is greater than the root node, it has to be inserted in the right subtree. Yes. So now we have created a binary search tree with 9 elements. Suppose we need one more element to be inserted. What do we do? So look at this example. Imagine that you need to insert an element 95 in an already existing binary search tree. So as usual, I told you earlier, you need to compare the elements with the parent node, and accordingly you have to move in the left side if it is lesser, or move it in the right side if it is greater. In this example, the item to be inserted is 95. So 95 will be compared with the root element 50. Since 95 is greater than the root 50, it will be moved to the right subtree. In right subtree, again one more subtree is there where 75 acts as a root. So 75 has to be compared with the item to be inserted 95. Since 95 is greater than 75, again it moves to the right side of 75. So there again you have one more element with 85. So now 85 will be acting as a root node, and the element to be inserted 95 will be compared with the 85. Since 95 is greater than 85, it will be inserted as a right child of 85. So if you look at the diagram, any item to be inserted, it will always get inserted as a leaf node in the binary search tree. So the next very important ADT in a binary search tree is deleting a node from the existing binary search tree. So as I told earlier, there are three cases when deleting an element from the binary search tree. The case one is the node to be deleted is a leaf node. So this is a very simple one. Imagine that in this diagram, there are 5 leaf nodes, namely 12, 30, 52, 70 and 85. So deleting the leaf node is very simple. You have to assign the node to the null and you got to delete that node from the tree. Case 2 is a node to be deleted has only one child. So in this example, let us take the node to be deleted as 12. 12 cannot be directly deleted from the tree as it has a child with the value 6. So before we delete the node 12, we swap or we replace the child value and the parent value 12, and then we delete the leaf node. So in this case, we replace the 12 with 6 and then we delete the 12, such that the child will not get disconnected from the tree once the parent is deleted. So moving on to the last case, the node to be deleted has 2 children. So here we have 3 nodes having 2 children each. If you take the root node 50, it has left child and right child. If you take node 25, it has 6 and 30 as their left and right child. If you take the node 60, it also has 2 children, 52 and 70 as their left and right children respectively. So let us take for example, like we want to delete a node 50, which is obviously again a root node. So what do we do here is, whenever we want to delete a node with 2 children, we need to replace that node with the smallest value in the right subtree of the node to be deleted. I repeat, whenever we want to delete a node with 2 children, we need to replace that node to be deleted with the smallest node in the right subtree of the node to be deleted. So here we are talking about to delete the node 50. So the right subtree of the node 50 has 4 values: 75, 60, 52 and 70. So the smallest value is 52. So we need to replace 50 with 52. And now the node to be deleted 50 will appear in the leaf node. So now you can directly remove the leaf node 50. So this is a special case. So repeating again, when you want to delete a node with two children, it is very simple. You need to take the smallest value in the right subtree. You need to replace that smallest value in the place of the node which you want to delete. And finally, you can delete that leaf node. So the next ADT is search ADT. Like the procedure what we followed for insertion, we got to follow the same thing. Imagine that the item to be searched is 60. We start searching from the root node. If the element to be searched is greater than the root node, we consider searching only in the right subtree, because the binary search tree property says that all the elements in the right subtree will have a value greater than the parent. So no need to search in the left subtree. So in this case, the search element is 60. The root elements holds the value 50. So we obviously need to search the element in the right subtree of the 50. So you no need to search the element in the left subtree. So only half of the search is enough to check whether the search element 60 is present in the given binary search tree or not. This is the biggest advantage, where the number of search is getting reduced when compared with the normal binary tree. As the name implies, binary search tree makes the searching process easier. So coming back to searching an element 60, we start with the root nodes 50. So since 60 is greater than 50, we move to the right subtree. Again, in the right subtree, we have a root node 75. So 60 will be compared with the 75. Since 60 is lesser, we move to the left subtree of 75. So there, now the root element is 60. The search element is also 60 and the root element is also 60. So thereby we stop the comparison and we conclude that element is present in the given binary search tree. This is all about the search operation. So the next ADT is find max ADT. So we know that maximum element in a binary search tree will obviously be present in the right side of the given binary search tree. So that is the property of the binary search tree. So if you look at this diagram, the maximum element in the given search tree is 50, which is obviously present as a last leaf node in the right subtree. So similarly, find min is again one more ADT in a binary search tree. As the property says, the smallest or the minimum element in the binary search tree can be found in the left subtree as a last left child. So if there is no left child, then the node itself is the minimum. So all the ADTs states that binary search tree makes the searching process very efficient, since we get a hint at each step about which subtree contains the desired element, like whether you want to move in the left subtree direction or whether you can find an element in the right subtree process. So in searching process, it removes half of the subtrees at every step. Also, when you try to insert or delete an element or a new node, the comparisons are made and it makes the insertion and deletion to speed up the process as compared with your array and the linked list. Thank you.